Imagine a photograph showing time itself, bending and twisting. Sounds like science fiction, right? But one sensational headline suggested that very thing. Capturing the first real image of time warping. This bold claim invites all our curiosity. Did we really freeze time on film? Or is something else going on? Hold on to your hats. Einstein's relativity tells us that time and space are inseparable, woven into a single cosmic fabric. A massive object, according to Einstein, drapes and curves that fabric, altering the flow of time and the path of light. If you're dreaming of capturing time warp, you'd aim at the universe's most extreme stage, a black hole or neutron star. Could our eyes, even telescope eyes, ever take a picture of such a spectacle? Maybe not time itself, but we can photograph its effects. Telescopes can't see clocks running slow, but they can see light being tugged and twisted by gravity. So if not clocks, what then? The truth is even better. We captured light's journey around a black hole. In 2019, the Global Event Horizon Telescope stunned the world with the first ever image of a black hole in galaxy M87. What you see is a glowing ring of superheated gas, but that ring's outline is honed by gravity's grip. It's as though the photo is an imprint of space-time itself being twisted and turned. Look closely. That may very well be our closest glimpse at time bending near a black hole, even if we're really seeing light on a twisted path. Think about that. Multiple radio dishes around the globe linking up as if forming a planet-sized lens. That's the Event Horizon Telescope. It doesn't capture visible light, but radio waves. It's like turning Earth into one giant camera. At the same time, the Hubble Space Telescope peers into the depths of space in optical light. Alone, each is powerful. Together, they reveal secrets about how gravity stretches light. Nothing supernatural here, just technology and theory showing us the extraordinary. Gravity isn't just weird, it's mind-blowing. Anywhere there's mass, space curves and time twists. A star punches a small dent in the fabric. A black hole punches a hole. Place a clock near a black hole, and its ticks would slow to a crawl. Place it far away, and it ticks normally. One day, in a black hole's intense gravity, could equal centuries outside. Now, you can't take a photo of a clock running slow, but you can photograph the outcome. Every image of a black hole carries this time dilation fingerprint. Remember the EHT's 2019 image? That glowing ring around darkness wasn't just a stunning photo. It was direct evidence of Einstein's warping of space and time. Switching from Earth-based dishes to space telescopes, Hubble has its part in the story too. Not to be outdone, Hubble once spotted a lone black hole in our own galaxy that cast a ghostly lens. It drifted in front of a distant star, and suddenly, the star's light brightened, like a candle flaring under a magnifying glass, then dimmed again. In effect, the black hole was magnifying the background star's light. By watching that dance, astronomers even measured the black hole's mass. Hubble took a snapshot of gravity in action. We see how gravity can steer light, and if gravity steers light, it steers time as well. Of course, gravitational lensing isn't new. Remember the solar eclipse of 1919? It was humanity's first proof that starlight was warped by our sun's gravity. Star positions shifted just as Einstein predicted. A century on, we see whole galaxies copied and bent in the cosmos. Hubble has unveiled these cosmic funhouse mirrors, galaxies appearing as arcs or rings, Einstein rings, created by massive galaxies bending light from even more distant objects. Every one of those images is a snapshot of space-time bending. Sure, we don't literally see time warp, but trust that the time distortion is there in the physics. Let's connect the dots. How is a warped light image like time warping? Think of space and time as a fabric. When you stretch one part of the fabric, you tug on the rest. An Einstein ring or lensed arc is the visual clue of space being stretched. Each photon on that ring traveled through more or less gravitational terrain. And because gravity also stretches time, each photon lingered a bit longer in some regions than others. So the image we capture is like a time capsule. It records differences in the journey times of the photons. We can't see slow clocks in the photo, but we see the imprint left by their slow journey. Return to that iconic black hole shot. Picture that glowing ring. Imagine it in golden light, even though EHT was detecting radio signals. Each point on that ring is from photons skimming the black hole's event horizon. Some photons shot straight out. Others looped around the hole one or more times before escaping. The black hole's spin drags space-time around itself, so photons on one side get boosted, brightened, while the other side is dimmed. In the grand movie of the universe, this ring is evidence that space is twisted and time is running unevenly at the edges. We may not see clocks ticking slowly, but we know from those photons that near the black hole clocks would behave very differently. And guess what? The story didn't end with M87. Just a few years later, EHT delivered an image of our own galaxy's central black hole, Sagittarius A. Once again, a bright ring from matter orbiting our galaxy's monster. The results matched beautifully with M87's image, confirming the physics. Now we have two extreme experiments side by side. Each pixel in these images is a clue about how space and time curve around enormous masses. When you step back, the big picture is staggering. Telescopes like EHT and Hubble aren't just taking pretty pictures, they're revealing the pliability of space-time. We're capturing light that has wandered through curving cosmic highways. A photo of that light is a snapshot of space being bent. So when you hear time warp photo, know that behind the sensational words is something profound. We're witnessing Einstein's drama on the grandest stage. There's a mountain of detail behind the scenes. Gravity even changes light's color. Climb out of a gravity well, and photons lose energy, shifting toward red, gravitational redshift. We've measured this effect in labs and in stars near dead stellar cores. For our black hole images, those escaping photons are indeed heavily redshifted. And time dilation means events near the horizon play out in slow motion for us. Imagine if we had a high-speed movie of gas plunging in. To us, it might look like a waterfall in slow motion. In reality, the image is a time-averaged blur, but our physics models tell us the truth is happening behind the scenes. In the end, calling it time warping is poetic license. We didn't literally freeze clocks. We photographed light behaving exactly as Einstein predicted. If space-time is a tapestry and a black hole a heavy stone, then our images are snapshots of that stretched cloth. We see the warp in the fabric, even if we can't isolate the time threads. The time twist is woven throughout. And isn't that amazing? This isn't science fiction. It's happening now. We once could only scribble equations about gravity and time on blackboards. Today, we have actual pictures showing their dance. We detected gravitational waves, literal ripples of space-time, just years ago. Now we have images capturing light locked in the grip of gravity. These achievements showcase human curiosity and ingenuity. Who knows what's next? Maybe one day we'll indeed film time itself up close. If that happens, we'd truly call it capturing time. So, while we haven't snapped a photograph of clocks running slow, we've done something equally spectacular. We've captured the fingerprint of gravity on light. We've captured the universe bending around massive objects. The title "First Real Image of Time Warping" might be a stretch, but that doesn't make it any less awe-inspiring. These images are our window into relativity's realm. If you loved traveling through space-time with me, smash that like button and subscribe for more cosmic adventures. Ring the bell if you want to be notified whenever we explore the universe again. Share this video with fellow space enthusiasts. What blew your mind the most? Let me know in the comments. I read and reply to every single one. Thanks for watching, and stay curious out there. See you in the next space adventure.